So the first thing I want to do is thank the other people who agreed to participate. Per Helander, Felix Para, Frank Jenko. They didn't have to do this, but they agreed to do it. And that was very nice, because otherwise I'd have been here all by myself. And the other thing I want to say is that this isn't, more broadly, we're going to talk about electric fields. That's really why I thought it was important for Per to talk. When we do gyrokinetics in the core, we normally assume that the electric field is small, the E cross B drift is much smaller, the global E cross B drift is much smaller than the parallel streaming. But in the pedestal, that's not true, and in stellarators, it's also important to keep that. So this was a chance to let you know a little bit about what's of interest in the stellarator community as well. So Bill already asked, who's this we? So I guess I should have said some things I think we have learned about stellarators, thanks to my students and visitors and so on. So some of you, have been to Vienna and have heard a lot of this. I'll apologize in advance. But some of the results have been corrected. There have been changes we've realized that matter, that we didn't quite get right. So let me start just to remind you. We have a stick, but I don't think I need the stick. Actually, does this work? Does that show up? No, that's not going to show up. Okay. So I'll have to use the stick. When we talk about a pedestal, what I have in mind is really a density pedestal. That'll become clearer as I go on, but it might be an electron temperature pedestal. But we'll talk about ion temperature as I go through this. And typically, we don't really know how a pedestal scales with poloidal Lama radius, but interesting pedestals can have the scale of a poloidal Lama radius, and that's where the electric field becomes really important, okay? So I'll try to make that clear as we go through.
Can I make a comment?
Yes, please. Yeah.
It's pretty clear it doesn't scale with poloidal Lama radius now. There's a lot of data which says it
Right.
scales like the poloidal beta, the square root of the poloidal beta times the minor radius.
Right. I don't disagree with that at all.
I think in today's tokamaks it's like the poloidal Lama radius, but maybe we bear in mind that it might be much bigger than the poloidal Lama radius.
All right. I have no comment on that. I know Phil has done a lot of work, and I know that.
Experimentally as well.
Yeah. But in CMOD, where we have some experimental results, and also I have a little bit of D3D results, and Per mentioned there might be mass results as well. You need an ordering that makes the electric field appear in lowest order, and this is the one that makes it do that. So why does the electric field matter? Well, typically, when we do axisymmetric calculations, we throw away the E cross B drift and we keep only the parallel streaming term. But in fact, in a tokamak, if the electric field is strong enough, like it is in the pedestal, these two terms can compete, and that's the ordering that matters in the pedestal. So what we have is not a large E cross B drift. We're not ordering the E cross B drift on the order of the thermal speed. We're really ordering the E cross B drift on the order of the thermal speed times the Lama radius divided by the poloidal Lama radius. So there's a B poloidal over B factor that's coming in. And the edge of tokamaks, typically Q is large. So epsilon might be a third or so, and you have a Q that might be 6 or 7. So actually B poloidal over B is quite small. So it's the geometry that's making the E cross B drift compete with the parallel streaming, or the projection of the parallel streaming. All right, so here's some topics. We don't have to get through all of these. This is the laundry list. So I'll tell you of a version of gyrokinetics that's useful in the pedestal. I'll talk about the ion temperature profile and show some D3D results. Talk about the implications of subsonic flow in the pedestal. and talk about ion and impurity flow with the finite E cross B drifts, and to show some comparisons with CMOD data where you can actually see these effects. Talk about the bootstrap current that gets modified out in the pedestal. And if we have time, we can talk about neoclassical ion heat flux, and we can talk about intrinsic ambipolarity, what that means, and the Rosenbluth-Hinton zonal flow problem as well. But probably, those are things we may not have time to get into. So here's the geometry and the coordinates. The typical toroidal magnetic field. And the canonical angular momentum is normally written this way, but it's handy to break it up into a gyration piece and a drift piece. Because we're interested in B over B poloidal very large, this gyration piece we're not really going to drag along. We're really interested in drift effects. So psi star is really psi minus IV parallel of omega for most of what is said here. That's the only feature we have to capture. That's the piece that really matters. And the other variables, typically we're using a psi star instead of a radial variable, a poloidal angle variable, a toroidal angle variable, energy and magnetic moment are the variables.
Is there any significance to the stars on zeta and theta?
There is, but for the purposes of this talk, there isn't. If you can write down gyrokinetic variables and correct zeta by a Lama radius gyration correction, but we're not going to worry about that here. Those are small effects. So psi star and zeta and zeta star, theta and theta star are the same for our purposes here. Should have erased those. So here is this is an old result, but I think it's useful to review these things. If you take and you assume axis symmetry and you use psi star as the radial variable, you get a fairly simple gyrokinetic equation in that case. It has time derivatives, and it has a theta derivative, and it has the collision operator. So if you were looking at neoclassical transport, you'd throw away the time derivatives, and you'd just be trying to solve the theta derivative balancing the collision operator. If you were looking at the Rosenbluth-Hinton zonal flow problem, you would throw away the collision operator, keep the time derivatives, and do a poloidal average of this equation to do the Rosenbluth-Hinton problem. But the difference in this equation, I'm using psi star as the radial variable because psi star dot is 0. It's constant of the motion. So this has the virtue that it gathers up the finite orbit effects and keeps track of them through psi star, because psi star is the constant of the motion. And I'll emphasize this now, but hopefully I'll remember to say it as I go through. What you really have to keep track of are these finite orbit effects. You have to keep the distinction between flux surface averages, which are done holding psi fixed, and trajectory averages, which are done holding psi star fixed. You have to keep track of that distinction to get the finite orbit effects right. So if you do this, look in the steady state, and you look at this equation, you can write down a constraint equation that the distribution function has to make the collision operator vanish, or you can go look at an entropy production analysis, and you, of course, come to the conclusion that the distribution function has to be Maxwellian. Well, that means because you're in the banana regime, there's no theta dependence to this distribution function. So you only have energy, magnetic moment, and psi star as your variables. So you have to make a Maxwellian out of those. And the only way you can make a Maxwellian out of those is using the energy and psi star. You get a toroidally rotating Maxwellian as the most general solution, but it has to be a toroidally rotating Maxwellian that has a slowly varying ion temperature variation. I think I've got it on here. So here's the toroidal rotation. Omega is this, and this eta times this exponential of the density. So that combination, eta and T and omega are all have to be slowly varying on the scale of a llama radius. So they can, they have to vary slow, I said llama radius, slow on the scale of a poloidal llama radius. They can't vary across the pedestal significantly. The corrections are, they're trying to be isothermal across the pedestal, I guess is the way I should say it. But that doesn't mean they're strictly constant. It just means that they're slowly varying across the pedestal. So the density profile can vary much more strongly than the ion temperature pedestal, the ion temperature profile can. And that, nobody likes to hear that, but there's actually, there's actually some data I'll show, but this is just an interpretation of what's going on. When you do the entropy production argument in the core, you do it flux surfaces by flux surface because things aren't varying very strongly. And so you can have things be a Maxwellian on each flux surface, each size surface. But when you're in the pedestal, you can't do it flux surface by flux surface. You have to integrate over the whole pedestal from the top of the pedestal to the separatrix, say. And to make the entropy production vanish, it has to be Maxwellian over that region. And so that's why that form that I wrote down is the appropriate form. It's important when you're doing a gyrokinetic code, you get to specify F naught if you're doing a local code. And it's important to know these things. F naught has to satisfy some equation. If you're doing a full F code, presumably then you'd find this out if you could do it all carefully enough. So here's some data from D3D that John DeGrassi provided me. The dashed line is the separatrix, and you can see the red, the black line is the density profile. The blue line is the electron temperature, and the red line is the ion temperature. And this is in a helium plasma, so they can actually measure the ion temperature directly. Normally, when we get ion temperature measurements, they're impurity temperatures, which are different than the electron temperature and the background ion temperature in some ways. But this is really the ion temperature that they're measuring. And you can see that that the variation of the ion temperature is not as strong as the density variation. Yeah?
So you would say that there is in fact not an ion temperature pedestal. You wouldn't interpret that rollover as an ion temperature pedestal. You'd say that that's just free streaming to the diverter. Or
well, this happens at the separatrix, right? Everything, we can't do anything up beyond there, right? Not.
But we assume that it's running down the field line.
Yeah, it's right.
So
Yeah,
there's no actual point at which you have good ion temperature confinement.
Right. The reason when we're inside the separatrix, we can do these poloidal averages that we do in the banana regime, but we can't do that, of course, once we cross the separatrix.
Sure, I'm not asking about Canadian theory there. I'm sort of asking you to say whether you would not consider that gradient a pedestal.
Oh, well, I think that's how you want to view it, okay? I mean, is that a useful pedestal? Perhaps, right? I mean, but it all has to happen beyond the separatrix. It's what? Yeah. But it's beyond the pedestal, but it's beyond the separatrix. It's not. Well, yeah, because you have stuff flowing to the plates. So, you know, the entropy production, does it have to vanish out there? Or it has to. It's what?
Then you'd have to ask why has it got such good confinement to be able to maintain such a good temperature gradient in stratigraphy.
Right.
To just pull the whole line temperature profile all the way down.
You have to wonder about what's the error bar on that dashed line.
Oh yeah, but well.
Could be a centimeter to the right.
I think in CMOD it's tough to locate the separatrix, but I think in D3D, you know, you're dealing with bigger scales in D3D. But yeah.
If I may add to the confusion, doesn't this another orbit also overlap into the critical plane?
Yes, it can bulge out into the, but it's
So that's the strong varying temperature.
I'm not going to disagree with that. I agree. you're asking to do the calculations and reasons we can't do this, but you know, you're going to have to do, the reason for codes is to be able to calculate something like that. But let's see, how do I want to say this? Initially, years ago when we were getting ready to write a proposal on trying to understand edge physics, people would say, well, we don't know the distribution function is Maxwellian in the pedestal. But then if you go off and you write and you make a code, suppose your code only has pitch angle scattering in it. You might find a non-Maxwellian solution with pitch angle scattering, should you believe it. That's not the full ion-ion collision operator. So this proof is based on the full ion-ion collision operator, and I would say that's a stronger proof than solving a model operator. Is it the last word? Well, who knows, right? Someone's going to have to face up to doing this region at the pedestal into the scrape-off layer at some point. That's part of the reason we're having this meeting, is to get you all interested in doing pedestals and scrape-off layers with gyrokinetic codes.
So just inside the separatrix, the first red dot circle inside the separatrix, what's setting the temperature there? It must be the equilibration with the electron temperature and whatever impurities are around, but that's getting weak because the density's falling fast. And then it must be the mix of the hot ions coming out and the cold ions coming in. And if you have a really well-conditioned wall, which is sucking up everything coming its way, then there's very few cold ions entering the plasma, and you can let that ion temperature drift quite high.
That's what, of course, the people like in Princeton are hoping to do with their lithium wall
This
experience.
seems to me to be strong evidence that that's happening, because if you just say, what is the ion temperature if I say that it's all going to run down and I've got some sort of sheath that forms, you get 250 eV, not 1.7 keV. So this is saying that there's very little backflow on this shot,
Okay,
I think.
okay.
But Peter, I didn't get the answer, and that was, what's the, for a trapped particle, what's the orbit width? Is it large enough to explain the separation between where the temperature falls and the separatrix?
Well, let's see. I don't think I can honestly answer that question, but let me tell you, the calculations I'll show, to do an analytic calculation out there, you have to assume epsilon is small like we always do in tokamaks, right? So then you're dealing with a trapped particle. Instead of a poloidal Lama radius, it has a square root of epsilon rho poloidal in it. So it's a little bit more localized. But that's not enough. I mean, really, the orbits are extending out, but they're not hitting anything when they extend out. So they're identified, a trapped particle orbit is identified with a flux surface that's inside the separatrix. It's just that it bulges out.
I know, but I'm trying to understand whether those particles you're measuring that have such high ion temperature there are actually have guiding center, or the center of their orbit is actually inside the separatrix or not.
Yeah, the
It's
center
only
of the
valence
orbit,
point
yeah.
that matters.
Yeah.
It's only the valence
It's only the,
point that matters.
right.
Well,
The-
no,
They can
Side-
just slide out and come back.
Yes.
I know, but is that
What
why
you're
this
measuring.
thing is sticking out?
Is
in
that
Yeah.
red dot because it's bulged out and then charge
Yeah.
exchange?
Is it really looking at
Yeah.
a pedestal line?
Yeah.
Well, I mean, we know a trapped, I'm probably repeating things. We know that a trapped particle, the psi star equals psi surface is the one that its turning points are on, right? So it can bulge out and sample out there. And now how do I do entropy production going beyond the separatrix? I don't know how to do that, right? Because I have to.
I'm not asking such a complicated question. I'm just asking whether that particle trajectory, in fact, bulges out all the way deep out into the pedestal region, and then goes back in and turns around inside the separatrix. Does
Yeah.
that happen or not?
In other words, are you saying that the separatrix temperature might actually be 250 eV, and we're just measuring
Yeah,
something with
exactly.
plasma leaking?
Right.
Yeah, that makes good sense.
It's a simple question,
Right.
I think.
The pedestal width's about 4 iron banana widths.
You-
And so it's not a million miles off what you said.
Okay.
Typically it's 4 or 5 iron banana widths.
Yeah.
So then there's really no ion confinement.
Yeah.
No, the ions are electrostatically,
Well, they're
statically
In
confined,
the
right.
pedestal, they're just
The ions are electrostatically confined, the electrons are magnetically confined is the lowest order way of thinking about it. And maybe I'll make these points when I do the show some of the
Yeah,
calculations.
You're reading more into, my question is a much simpler one than you were trying to answer, I think.
Oh, well, but the ions do have the ability to bulge beyond
I
the
know.
separatrix,
The question
sure.
is how much can they bulge?
Right, yeah, and,
You have the polygonal radius up there. It's 10 the polygonal radius.
yeah, where is it? 10 millimeters, so
Where's that? Where do you see that?
that's 2,
5 maybe?
yeah,
So 2 rho is 10 millimeters.
right, so,
So what's
so,
this?
so this is
Meters.
in meters,
So one of
so what is it? This is
the
5 centimeters,
So a fifth of between two tick marks.
so it's pretty narrow,
Well, that drop is narrow.
Yeah.
yeah.
So yeah, all of it.
But I mean, I think when they do the eater modeling, they would make the pedestal inside the separatrix. I don't know, how would you probably?
Probably put Ti equals Ta.
Yeah, yeah. I mean, that's what we do on CMOD. We take Ti equal Te or Ti equal Tz. But when you get near the edge, you have to start wondering about some of these things.
Yeah, so it looks like it could be comparable to the long radius, or to the banana.
The rapid fall off region.
Well, no, the sticking out into the thing.
Oh, yeah, it could be comparable to that one. Yeah. But I remember when Jim Hasty visited us at CMOD years ago, he tried to point out to them that Ti didn't have to be equal to Te, and they objected strongly to that. And he went back and did things carefully and finally made some progress convincing them. But after Jim left, they promptly ignored these things because Jim wasn't there to remind them anymore. Okay, so here's the simple-minded way to think about what's going on in the pedestal. You have a flow of the ions on a flux surface. It can be have toroidal and parallel components. This UI is the piece we would calculate from neoclassical theory that depends on the ion temperature gradient. And omega I is this combination that you get from pressure balance. If the electric field didn't matter, and you put in a gradient here, a scale length that was the poloidal llama radius, then you would get sonic flow. You would find that omega I R over VI was order unity. When they measure flows in CMOD and other devices, they're subsonic. So what has to be happening is that these two terms have to be trying to cancel in some lowest order sense. That is, the E cross B and the ion diamagnetic drifts are trying to cancel. That means the E cross B drift and the electron diamagnetic terms are trying to add, and so you get electron currents that are, electron flows that are near the ion sound speed. So you have the simple picture of ions trying to be being electrostatically confined and electrons magnetically confined, and that seems to be a pretty happy state. To the extent we believe H-mode pedestals are good. This doesn't mean this happens in an internal transport barrier. Life seems to be very different in those cases. Okay, so this is just reiterating what I said at the start. So this means when we go back and look at some of the neoclassical calculations that were done originally, or we look at the Rosenbluth-Hinton zonal flow calculation, the residual calculation, what we really want to do is try to treat the E cross B drift the same order as the streaming term in redoing those calculations. Now, that would be hopeless to do, except we have epsilon as a parameter we can expand in. Now, I know epsilon is a third, and we're expanding in the square root of a third, but that's how life is in plasma physics, tokamak physics. So the results that I'll show you, they clearly have to be improved by doing these things numerically, but they are useful for testing codes to make sure they're doing the right thing, all right? But they're also useful for understanding what's going on. They are, I agree, yeah. But you know, we always say, you know, you're making lots of approximations, but that's how life is. You know, we're big boys, we have to make approximations. We know we can't solve these problems exactly, if experience has told us that. And by making this rho colloidal much larger than rho assumption, we're decoupling the neoclassical and classical effects. We only care about drift effects here. So what are the interesting physical effects that take place? Well, because the potential is trying to be a flux function and the particles are moving on surfaces of constant psi star, as a particle drifts around, it can be trapped by the electric field. It's not just magnetically trapped anymore. So the trapping depends on electric field as well as on magnetic field now. Also, there's a shift. In the usual case, the trapped, here's the Maxwellian, the surfaces of constant speed. Normally, you just have lines of constant pitch angle through here, but because of the finite E cross B drift, things are shifted away from symmetry, and the bigger the E cross B drift is, the further they're shifted out onto the tail. So you expect in some cases you'll see this as an exponential decay because there'll be very few particles. Anything that depends on trapped particles, you can get a small population of trapped particles because they've been moved out onto the tail of the distribution function.
Earlier you made the argument that this U was going to be about a 20th of VI, and here it's bigger than 1.
Did I say a 20th?
And
epsilon
over Q, and epsilon was about a
No.
Q was 6.
No, I mean, the point is that you're using the B colloidal over B is what, a 20th? So I don't need a very large E cross B drift to make it compete with the streaming.
But it's going to be bigger than that.
But that gives auto-unity effects when they compete. So let's see, I've said all of those things. Okay. And so the particle dynamics is really very different in the pedestal than it is in the core. So here I'm just reminding you how neoclassical theory works. We don't have to spend a whole lot of time on it. It's the ion temperature gradient that's the drive. We have to solve this transit averaged equation to get G. But now when you do this transit average equation, you have to do the transit average holding psi star fix. It's not enough to do it holding psi fix like you would do in conventional neoclassical theory. Okay, and then you use moments like you do standard neoclassical theory. So this is just to tell you a little bit about, this may be more than you want to know, but what we do is we take a quadratic potential well. And you can imagine if it's quadratic, you could write this flux function psi, you could expand it around psi star, and you only have to go to second derivative, and the second derivative is a constant. So this notation means phi is a function of psi star. This means it's a function of psi. And just to confuse things further, this U star is a function of phi prime star, which means it's a function of psi star. But you have to remember that B has some variation in here. So you have to keep track of that when you're figuring out the trapping and so on. But you can use this combination is still a constant of the motion, and you can get equations that describe these orbits. And so I'll show you one example. The equation has in the coefficient of the streaming term the V parallel plus U from the E cross B drift. So the left-hand side here is in the original variables, psi variables. But you have to write, to do the trajectory averages, you have to write that in terms of the starred variables. And you can show that this relation holds where psi, where S is the orbit squeezing factor and U star are related. So you have to keep track of these differences. You go crazy trying to keep track of them, and we've probably done it wrong more times than we've done it right, but I think we have it all sorted out now. And the handy thing that you're shooting for is to use this epsilon expansion, small epsilon, so you can get something of this form. If you were doing the standard calculation, W would be 1/2 V squared, and you'd have a pitch angle and a speed as the variables. So by analogy, you use W and a generalized lambda as the pitch angle variables when you do these calculations. And here's, again, this picture in velocity space. This is the standard case where you do you just keep track of pitch angle scattering across these lines of constant pitch angle. But in this case, the pitch angle variable becomes more complicated. The trapped region has more complicated boundaries and is shifted down. You have to keep track of that. And it's not enough to just keep pitch angle scattering. Now you have to keep energy scattering. So we use the collision operator that Ian and others developed here. So a result. Okay, I want to show you that something actually comes out of this. So if you go through and do the calculation, you get the standard result, but there's a factor here. This J in the core would just be 1. But now with the electric field term in there, it drops off from 1 and changes sign. 0, where the hell is 0? There it is, right there. So it changes sign at about 1.2, I guess it is, and goes to the other side. So if this U over VI can get to be order unity, you can get to see some interesting results. And that's an important thing for a couple reasons. One, we have some CMOD data that shows this effect. Two, and that the sign changes to the sign of the Fehr-Schluter regime when it goes negative. So this seems to explain some observations and measurements in CMOD, and also this is going to change the pedestal bootstrap current. Right? So let's see if here's some CMOD measures impurity flow, of course, so you have to relate the impurity flow to the ion flow, and they've done all of that. They made some comparisons with the peak measured velocity from theory, let's see, which one? Yeah, from theory, Fehr-Schluter, and from the experiment. And the points seem to cluster around the right line. So with the measurements where the pedestal was sort of a collisional pedestal seemed to make sense. But then when they did the measurements, when they got the pedestal to be more collisionless, and it was actually in the banana regime, then it wasn't working so well when you compared it to the banana regime. There don't seem to be any points there. So we were trying to, we were actually working on this problem while they were making the measurements. So, but there's clearly a problem in the banana regime. So here's more detailed measurements. There's a couple representative cases, one a pretty good one and one not great, more typical. They don't have a whole lot of data, but you can see you get the measured is the black and the red is the analytic expression. Let's see, is that right? Sheen peak, yeah, measured peak. Okay, so you can see that you're picking up the peak to some extent, and when they plot just the Fehr-Schluter measured points versus the theory points, they tend to cluster around the right line. Looks like it's doing the right sort of thing. You can also try to get the peak in the plateau regime, which is the shaded region. And I had a visiting student who did this calculation. And you can see that it really doesn't matter whether you keep the corrections in that case from the U over VI. It turns out that this J thing for the plateau is really pretty flat. It doesn't change sign, and nothing terribly exciting happens. But in the banana regime, it does matter. If you look at the, let's see, this is the banana regime without the electric field term, the standard result down here. And it doesn't pick up the peak that they observe. And so when you put in the electric field correction, you do get this peak. And instead of getting these black points over here that are nowhere near the line, you get points that are clustering nearer the line. Now, is this perfect? No, it's not perfect. I mean, the measurements aren't perfect. The theory isn't perfect. There are approximations that go into it. But it seems like there's a real physical effect there that matters and is important to keep. Okay, well, why does it change the bootstrap current? Well, the bootstrap current is electrons. You don't expect the electric field to matter for the electrons because they have a much higher thermal speed. But the point is that the electrons feel the friction of the ions. When you do the neoclassical calculation for the electrons, there's a drive term that's the difference between the parallel flow of the ions and the parallel flow of the electrons. Well, the parallel flow of the ions has changed because of this J factor. So wherever there's a temperature gradient term, you expect the J factor to enter. So here it is. You have to write the pressure as the total pressure when you put it in. So there's the J factor. This is the large Z result. This is arbitrary Z result out of Pear's book, but just putting in this factor. So you actually get a modification to the bootstrap current in the pedestal, which can matter for stability calculations. Stability calculations are terribly sensitive to the details of these things, and it actually enhances the bootstrap current in the pedestal. Because remember, this sign is going to change when U over VI is a bit bigger than 1.
Isn't the sign in front of TI prime change as well, when you go to finite aspect ratio? I think it isn't this.
That's a claim. Well, I will object to that because those expansions are done, they're square root of epsilon expansions using only a pitch angle scattering operator. And the pitch angle scattering operator is only a lowest order operator. You really need a better collision operator. So I think the jury's still out on that. But it could be, there could be something.
Epsilon goes to 1.
You know the answer at the epsilon going to 1 limit, I agree, right.
It's definitely plus in that, isn't it? So it's going to change at some.
Someplace in between. Yeah, to that extent I would agree, yeah. Yeah, I just don't believe in detail the square root of epsilon
So
corrections.
your statement about whether it enhances or diminishes the bootstrap current is going to depend on the aspect ratio.
You bet, right. But, you know, there's only, we're not, there are real questions of, we have to make approximations on the collision operator. There are, well, this is getting into a detail you want to know. Should I really believe that 1.17? I don't know, you know. But that's the calculation, the way it was done by Rosenbluth eventually, and we've mimicked the calculation to make sure we get the standard results. Yeah.
So what do you have to do to have bootstrap current in the pedestals back for MHD stability? Can you tell experimentalists how to minimize the bootstrap current?
Why is it bad? It just has the wrong sign?
That's the king color.
But it's good for ballooning, you get it right.
You tend to get bad elements. You might get a higher pedestal, but you get bad elements.
But is the drive from the pressure or the ion temperature gradient, or do you know which? Okay, yeah, I mean, these are, I don't know the answers to these things. We certainly haven't attempted to look at anything like that. We wanted to keep you and Phil busy.
It'd just be nice to have a knob to control the bootstrap current that's independent of the pressure profile in the or the temperature profile in the pedestal. It's providing such a knob.
Well, to the extent you have any control over the electric field in the pedestal. I mean, the electric field really is a knob in the experiment, but we really don't know how to exploit that at this point, other than by trying to put momentum into the plasma. And these, I should emphasize that in fact, you know, this behavior in the pedestal, this radial Maxwell-Boltzmann behavior for the ions, this really isn't momentum transport. This is just a nice equilibrium. Momentum transport causes there to be a difference between the E cross B drift and the ion diamagnetic drift. It's that difference that momentum transport determines, and that would be a very hard calculation to do. So this isn't really of interest because we don't really care about heat flux, but you can do the heat flux calculation, and it does illustrate this exponential dependence comes in now because the heat flux cares about the localized piece of the distribution that comes from the trapped particles and the barely passing particles. That's why you see this exponential behavior here. That's it just falling off. Here's the orbit squeezing factor. The orbit squeezing factor is different than people have claimed in the past. You really have to keep track of these things quite carefully.
You mean Shang?
Yeah. It's what?
How's it different from Shang?
I think the S is in the numerator. It's the three, maybe it's an S to the 3/2. I can't remember. Is that what it, the difficulty with, and this is really a subtle issue. I don't know that we should get into it, but this has to do with the properties of the collision operator, whether when you preserve the momentum conserving property of the linearized collision operator, you do it holding psi fixed or psi star fixed. And it only has the right property holding psi fixed. And they did it holding psi star fixed. And this is an incredibly subtle issue, all right?
You said the energy scattering is important. Does it change the scalings or does it just change the numbers?
Just changes the numbers, yeah. You pick up, slightly different factors. Okay. And it's obvious that the heat flux, by the way, I'll put this back. All of the, this is a good point to make. I mean, we all worry about shear in the electric field, but in the pedestal, it's really the electric field that matters. The shear is just a geometrical thing. There was no shear that entered into the expression for the ion flow, but it does enter into the heat flow, but it's just a square root of S. It's not that big a deal. But the electric field sensitivity is, of course, really there because you get this exponential behavior.
Presumably we're worried about shear for toning and suppression, not for
Right. Yeah. But we do. But the ion flow we do care about. I don't think, the neoclassical result for the heat flow is probably not terribly interesting. And I should try to finish here. What else do I have? Oh, okay. So actually the first thing we tried doing was the Rosenbluth-Hinton calculation for the zonal flow by putting these electric fields in because we thought, that ought to be easy. There's no collision operator. Well, it turns out not to be so easy. And I've shown this result before, but the reason it's not easy is that there's an imaginary term that corresponds to a shift between the perturbed potential and the perturbed density. And getting this thing right has been a nightmare because you really do have to keep track of the orbits to extraordinarily high accuracy to do that. And Matt Landreman was finally the one that figured out how to do that. So we have an earlier publication where we claimed to do it, which we quickly had to write an errata saying we did it wrong and that you should set S equal to 1. But Matt finally figured out how to do it, and that's been published as well. So you have this thing this expression you could check against a code. If you had a gyrokinetic code that worked in the edge, you'd have something to try to check it. Is this a realistic thing to check? I don't know. But I think, it's of use for that reason. I don't know that it's used for, we've had discussions earlier in the week, how useful this thing.
How to do a gyrokinetic code that works in the edge, right?
It's what?
You can tell us later how to get
Well,
a
I think,
gyrokinetic code
I mean,
that works in the edge.
Felix is going to give us a 2-hour presentation on that, but he's compressed it to 15 minutes in order to.
Oh, he has a great record.
Now, these are really hard problems, of course, but we're hoping to whet appetites here. Okay, so I should quit. So this is just summarizing these things, but we're going to have future festivities here. In a moment, Per will get up, but are there any things that we haven't covered that I should try to answer with my limited knowledge of these things?
So Jim and Barrett ran a series of simulations of L-mode-ish parameters, and they slowly ramped up gradient and saw that the plasma flopped over into this balanced pressure in E field balancing each other, and that was with a two-fluid Brzezinski. To what extent do the subsequent results from a code that's a Brzezinski code hold? Because the electric field is ordered in some way, and so can it really pick up any of this? I mean, it's a finding that you confirm that kind of confinement.
Yeah, it's clear.
But then, do we have to work a lot harder to go beyond that?
Well, as I recall, that was a slab code, or am I remembering?
No.
Oh, you did it in a torus. Okay, I'm thinking of the wrong paper then. Okay.
Magnetic pumping that was causing the balance between the.
Yeah.
Okay.
Magnetic pumping it.
Okay. Let's see that. I mean, in the Fehr-Schluter, because it's a collisional description, I have to equate it with a Fehr-Schluter description. These effects we haven't seen any way to make them show up, but I don't see any reason why that wouldn't be still a desirable state to have the ions.
It's a great state.
Yeah.
The question is, when we
Helmholtz is stable in that configuration.
Yeah, there's lots of great things
Yeah.
happen in that in that state, and the question is, to what extent can we think about those with the current tools before we take into account these shifts and other issues?
Which shifts are you?
You had the whole distribution being shifted by the electric field.
Oh,
the
okay,
exponential effects,
okay,
lots
yeah.
of things that we
Yeah,
don't-
that happens when you
clearly
go into a
don't know.
a more collisionless limit, of course, yeah. I don't know, I mean, the real problem in ITER and in D3D, these tend to be collisionless edges. We know that. And CMOD is sort of a special case because it can span all of these regimes so that we can look a little bit into each of the regimes. But do we know, I mean, CMOD seems, the turbulence in CMOD seems similar to D3D. I don't know. I guess we need a better understanding of what the turbulence, the codes all have problems running out beyond 0.8 or so you're not really
Well,
running.
No, this was studies
but-
centered on two-fluid Brzezinski looking in the
Right.
region where gyrokinetics has not successfully
Mhm.
treaded.
Can you remind me, what did it have for the viscosity in it?
It was straight up Brzezinski.
Did it have the full collisional viscosity as well as the gyro viscosity, or?
It had new II as well as, I mean, it was more or less straight out of the plasma formulary, implementation of Brzezinski.
Okay, so that wouldn't have had, I mean, yeah, it really doesn't have the momentum transport into the extent of having the Fehr-Schluter regime.
Right.
Yeah, okay. So I don't know, that probably didn't play a role, though. That probably didn't matter a whole lot in there. It was probably the balance between the E cross B and the ion diamagnetic flow that was what did you do with the ion temperature profile? Did it vary strongly or not?
We evolved that.
You evolved?
Turbulence.
Okay.
Turbulence.
Okay. So you started with an equilibrium in which the ion temperature varied as strongly as the density? I mean, I think that's probably allowed in the collisional plasma.
This was a flux tube code. We had beta I and 80E 1-ish.
Yeah, okay.
We vary.
Yeah.
We definitely varied. We were trying to explore whether you get the grad TI instability,
Mhm.
the relative role of that compared to resistive ballooning and that sort of stuff. So we explored that.
Okay.
I mean, the parameters of the edge are very different from the core.
Oh, boy, are they? Yeah.
So, that changes a lot of
Right.
basic phenomenology on the turbulence.
Right. I mean, it's still unclear to me how strongly the ion temperature is allowed to vary in these compared to the density in the collisional plasma. I mean, part of me argues that it can, and part of me argues from neoclassical theory that when does the small correction to the Maxwellian become a Vada unity? Well, so it's not clear what the right argument is there.
So let me ask you a
Yeah.
question, keeping in mind I've been out of this area for a while.
Well, it's only fair, Jim. I ask stupid questions in the reconnection all the time, right? But you'll at least ask intelligent questions.
Well, I don't know about that. I remember, so you were talking about D3D and CMON and all that. And I recall when NSTX was first proposing their experiment, they were, the parameters of that machine, prior to building it, were so dramatically different than everything else. So they sent me these numbers for the edge, and the predicted numbers for the edge, and I was gonna put it in to see what we thought. And they had beta. The effect of beta was enormous. The effect of beta, in which beta times big R over the gradient scale was enormous by their estimates. And so it was off scale compared to every other machine we'd ever looked at.
Mhm.
And my recollection was that after they got NSTX running, the parameters are very different. The length and the edge, my recollection is the scale length was very large compared to other machines.
The scale length of the density variation, or
Yeah, at the edge region.
okay, do we have
So,
someone here from?
In terms of, now maybe that's passe at this point because I haven't been following this, but, you know, in terms of trying to separate, identify physics by separating, by looking at machines with very different parameters so that you can tell trends. I'm not seeing that NSTX is being used, and so I'm wondering whether that the data from that machine is being ignored, whether people are trying to think about the differences or not.
We should say mass since we're in England.
Right.
Same thing. Yeah.
The simple answer is I'm probably ignoring it, but I'm not aware of measurements of the flows in the detail that we have in CMOD at this point. Sometimes I don't know if I've talked to anyone or masked NSTX that's told me they have flow measurements. Sometimes people have flow measurements and they haven't analyzed them yet. And I don't know what the state is in NSTX. Per mentioned, I think, did you mention that they had some measurements in MAST or
Of what?
of the flows in the pedestal?
Well, I think it was me that
Was it you? Okay.
So they have measurements in mass, and what they have shown me is that the pedestal is comparable to the eye radius, and the density drops very strongly, and the eye temperature radius is exactly zero.
It's flat.
The collision is flat.
Flat.
So,
Flat. Yeah.
Does that mean there is no ion temperature pedestal? Or does it mean that it resides entirely in the pedestal?
It must reside entirely in the scape of layer in my guess.
It must be what, I'm sorry?
Entirely the scrape off layer.
The pedestal must be in the scape of layer. But
It
it
goes
is
way out, they've measured it way out, and it's still flat. So there's some uncertainty about that, it's not say controversy, but some uncertainty about that result.
okay.
Because it stays flat way outside. So
I see.
It's my,
so I can't.
Flat and at what level?
but you,
I can't remember the details, but yeah, I think the hot filament's way out in the scope there.
So I can't claim a victory for theory at this point.
Yeah, but the
Yeah.
crux of my question is simply that, you know, it's hard because if you look at NSTX, or if you look at D3D and CMOD and Aztec's upgrade, I mean, they're so similar in many ways. I mean, I realize that CMOD has got some big differences, but still, you know, it's very hard to distinguish. While if you bring in a different animal, sometimes you can learn, and that's
Yeah.
what
I mean, one of the things, though, you have to keep in mind is we're taking advantage of B colloidal over B being small, and that's not necessarily going to be the case in MAST and NSTX. So life is a lot more complicated
right.
there.
but
Yeah.
In some sense, that's the point.
Yeah, but we can't, you can't do anything analytically, so then you have to do,
but,
right.
you know, I'm asking a more general question, and that is, where are we going? In other words, there was some discussion at the beginning of your talk about the scaling with the pedestal with parameters.
Yeah.
And so if you've got a machine in which it's true there are differences, but the differences are good because then maybe you can use that additional data to sort out this issue of how does it scale with the colloidal arm radius or the hybrid of colloidal arm radius and the
Right, but that's a very, very hard question.
It's done. Mass data is
Yeah.
taking those scaling those the mass pedestal with scale like root base colloidal. Well,
It's root beta colloidal.
Root base colloidal times minor radius. So that data is taken.
That data is-
I think NSTX, I hesitate to say, but I think NSTX can't resolve that pedestal so well, and Thompson scaffolding isn't sufficiently good to resolve the pedestal in a lot of detail.
Okay.
Whereas it is on mass, so mass data is definitely good.
Shall we continue with the festivities so we can?
Once more
Oh,
remark
yeah,
or
yes,
question.
go.
I mean, the toroidal flow exhibits some kind of complex pattern in the scape of layer.
The what? The
The toroidal flow, the toroidal velocity has rather a complex pattern in the scape of layer.
No, well, were you here for Ian's talk, Xavier? The toroidal flow is actually pretty benign. The colloidal flow has structure in it. Ian showed Rachel McDermott's measurements of these, the impurity measurements with boron, and what she did was measure all of the terms in the momentum balance for the impurities in the radial momentum balance, and then backed out the electric field from those measurements. And when you make those measurements, you're measuring the logarithmic density gradient, the temperature the impurity temperature gradient, the colloidal flow and the toroidal flow. There isn't much structure in the toroidal flow, but in the colloidal flow there is structure.
But how can it be? Because you have to match the boundary conditions somewhere.
No, not inside the separatrix.
And I'm talking about the stepper.
Oh, yes, yeah, Brian, yeah, we try to do things outside the separatrix. It's much harder
But my
there.
point is that at some point you have to match the solution in the stepper layer, which is kind of colloidally asymmetric, right? And what you find in the pedestal.
Well, I'll give you my interpretation, which Brian LeBombard would probably be horrified at. But if you take Brian's measurements near the midplane, don't go too close to the diverter plates, then what you tend to find is that you can match the, let's see, there's a piece of the electric field that if you change from low null to upper null, it'll change sign. So let me call that an asymmetric piece. That piece tends to vanish as you go to the separatrix. And so then things can match on to what's in the core. But once you get out in the separatrix, the flows in the scrape-off layer care about where the X point is. And they of course care whether the magnetic field and the current are in the same direction or opposite directions. CMOD runs with the current and the toroidal magnetic field in the same direction. D3D runs with them in the opposite direction, so you have to start worrying about all these things as well. I don't think there's any obvious inconsistency, but people certainly have their own interpretations, and I wouldn't expect Brian to agree with my interpretation. Brian has done a lot of measurements out there.
What would you say, I'm not sure I understand what, would you say that the situation is symmetrical before you reach the separatrix?
Well, I would say once you get to the separatrix, then because you have streaming to the plates, which is on the bottom in CMOD, then you pick up an asymmetric piece because it knows the flows know about the bottom is different than the top. And so the behavior out there is not, it can match smoothly to the core, but it's more complicated. People like to think, oh, whatever's going on in the scrape-off layer is the boundary condition for the core. But I tend not to think that way because I think there is this other behavior going on in the scrape-off layer that's simply due to the diverter and the flows into the plates that cares about whether it's a lower null or an upper null. So you get additional flows that are generated by that.
Here, this is a little off topic, but there's a weak pedestal even in L mode. And I assume that's not particularly well understood.
Not by me, but this certainly won't help you there because the electric field would be too small to do anything. Yeah.
Seems like a good
Yeah. Well, I mean, there are lots of things we can explain. We're trying to focus on something we might have a chance of providing some insight on. Okay, shall we get on to pair? So pair, the pair is going to tell us about stellarators where electric fields really matter. And this is, in here I've tried to stress the importance in the pedestal of keeping the global E cross B drift along with the parallel streaming in the pedestal, but in a stellarator, even in the core, you have to worry about these electric fields because the electric field is adjusting to make sure that the ions and the electrons get out at the same time, and hopefully Per will have time to get to that point in his talk. Tells us about how they do. Okay. Knowing that I would talk too long, is that?